So welcome back. Next up, we've got Taylan Cemgil from DeepMind.
Well, thank you very much. So maybe I'll introduce myself first. I'm a research scientist in the Science and Strategic Initiative. So DeepMind is organized in different kind of organizations. There's foundational research, there's generative AI, and I'm mostly dealing with scientific applications of machine learning, currently mostly LLMs. Before joining DeepMind, I was also an academic who made the transition in 2019, which was also a little bit forced due to some political situation in the country. And before that, I was in the signal processing lab, here in Cambridge, mostly working on Bayesian signal processing. So in DeepMind, I have been working on adjacent topics to uncertainty and uncertainty quantification, mostly related on robustness, essentially in the intersection of how can we bring methodology more towards products in some meaningful way and can make an impact in theirs, which is, to my surprise, coming from university, sometimes turns out to be much more difficult than you would have imagined. Here, I will mention some of the work related to selective prediction, hybrid model evaluation, without going too much into the detail, and I will focus mostly on evaluations under uncertainty. Of course, DeepMind is an extremely large place, so there are a lot of work still going on uncertainty. This is more my personal journey, or mostly things that I'm kind of familiar with. And most of the time, the ideas that I put are myself, not necessarily, of course, DeepMind's. So I try to think about tying a little bit different works that I have been doing, or we have been doing with our team in DeepMind to this topic. So a little bit talk about, because this is Isaac Newton Institute, one of the first summer schools I ever come was here actually in, I think, '98 on Bayesian signal processing. So it was one of the times when probabilistic machine learning was flourishing. There was a lot of interaction, people were working previously on neural networks, but then probabilistic thinking was coming to the center of things. So it was really an approach that everybody was, very kind of excited about. And the nice thing about it, it is, of course, intellectually appealing. It's a coherent framework. It has its roots in statistical mechanics, etc. And information theory is a very rigorous subject. And I think, it was also, I think one of the David Mackay here in Cambridge was also one of the more influential people to bring it. Of course, there are, of course, other folks there. So the nice thing about, of course, the probabilistic approach was that uncertainty is fundamentally baked in. So if you can come up with the exact model, then if you do inferences, then you are basically done. Of course, the problem there is, building those models was the main bottleneck. Over time, of course, many tools have been developed, from graphical models to probabilistic programming, etc. But still, the inference in this approximate models was always a bottleneck. Most of the time, the research effort was going into there. In a sense, the deep learning era come up to 2010, and many people are aware of that. It's in some sense, modeling the algorithm directly. It's not really thinking about the model and not thinking of the inference. In a sense, you lose control. So defining basically what the problem is turned out to be basically curating a labeled data set, which in a sense comes close to defining what a difficult task is. So for instance, I work in source separation, when two sounds mixtures are mixed, how can I kind of separate them back so that they are different sources? You can write a physical model and then try to turn it into an inference problem. And that is somewhat physically guided, but if you are talking about object recognition or logical inference, it was talking LLMs, when do two sentences mean the same thing, etc. Those are most easily done by just showing examples, and we humans also do. If you want to explain what a concept is, you provide examples, and it turns out that this particular approach has been really quite influential, and it was scalable. So. And in 2019, about the time I basically came for a sabbatical to DeepMind, Richard Sutton, who was a prominent researcher in reinforcement learning, had written this one-pager, like the bitter lesson. Basically, it says that general methods that leverage computation are the most effective and by a large margin, which is, in essence, in stark contrast to what based on probabilistic machine learning, to some extent, was trying to do. And he was really saying that, like, searching and learning, and its most fundamental, are the way to go. And of course, many progress which was done in DeepMind seems to actually support that. Okay, like AlphaGo, AlphaZero, those are all agents which play much better than human experts. And there's also some parallel innovation in kind of a language modeling. Of course, has some kind of history in the statistical modeling of a language, etc. In the past, there were also similar kind of improvements, but most of the approach basically, essentially like transformers, if you can view it as some way of parameterizing a retrieval algorithm in a vague way, and then you connect things together, and then when you frame it as a next token prediction problem, then you can actually use the representation that learned to solve several problems. So it was really benchmark driven, so it's kind of beating everything up. So that was quite interesting. And also, is this red light? So here, as you see, every progress, like this is an official DeepMind slide, apart from AlphaFold, is actually a kind of a language model innovation. So it is an extremely important line of research, which, in a sense, didn't have too much concepts of probability around. Okay, then there was an interesting debate between UIT, who was, he was at that time both in Oxford and DeepMind, I think he still is, and Richard Sutton. So the idea was, or the question was, do the agents, or do we even need probabilities? It was and EY was arguing for the probabilities are good. Sutton, following his bitter lesson, you don't need probabilities. Why do agents need probabilities? If it's needed, they could maybe infer it from basic principles. But at the end of the day, Bayesian inference is something that you can derive from basic principles, some kind of a game theoretic argument. So that was a quite intriguing thing. So it's an interesting question. Do you need at all uncertainty quantification or probabilities? So that was, and this was kind of unsolved. So in this workshop, probably I should say somewhat yes, but with a caveat. So for instance, this is AlphaFold prediction for proteins. And one of the important uses of AlphaFold is, of course, predicting protein structure. But the color that you see in here, I've personally forgotten which one is the prediction and which one is the ground truth. There's uncertainty there as well, but this color is encoding, in a sense, this particular per-residue confidence score, which are actually quite important. So, in a sense, given the structure, maybe there is really uncertainty where the position will be, and that has to be characterized by the model. And one of the important things that the team has to work on is really making the scores useful so that it can be used in practice. Another work which I was partially involved is watermarking. So if you generate a lot of text from the LLMs, you want to also make sure that you don't feed that back into the training data. So you want to actually detect it somehow that it was on bulk LLM generated. And here, of course, some basic ideas from information theory, etc., are important to build such a watermark. Basically, you bias the random number generated in such a way that you can actually detect a generated sequence from like n-gram statistics. But you have to also prove that on average, if you, for instance, integrate over all possible random seeds, doesn't really change the LLM distribution. So in a sense, you don't change the quality, or you don't change perceived quality, but you can actually have some ways of detecting that it is actually generated. And it was kind of a successful product like SynthID. There, of course, concepts from probability are important, but in essence, all these concepts are like post-hoc. So the capability of the model is there. The model is generating the text, but what we are trying to do to make it actually adapt to reality is actually needing probabilistic concept. So I think there is a pattern in here. Another topic which is also touched upon is evaluation of LLMs. For instance, LLM as a judge, or what we call critics, etc., are quite important. So if you deploy a model like Gemini, you want to check if these generated sequences are maybe factual. And they depend heavily on, again, LLM as a judge, because there is no way, even if we, for instance, make the problem very specific, for instance, like entailment type of problems. Entailment is roughly saying that if I utter two sentences, do they roughly mean the same thing? Is one somewhat maybe the summary of the other one? So that is and you have to still rely on a particular LLM for that. And the accuracy of that LLM is quite important. Like, how can you then measure it? Of course, you can do a lot of, like human evaluations, but this is not ideal. Also, these models are very good. So can we also use the model to judge itself? So there's some kind of recursive loop. But this problem can be solved by hybrid evaluation. So you basically collect very few human labels and a lot of synthetic labels, and somewhat use statistical arguments for variance reduction. And you can actually get quite a bit of improvement, sometimes tenfold better performance, in the sense that instead of rating 200 times for the same prompt, you can only rate 20. So those are quite important and are related all to uncertainty quantification. So I will go a little bit on selective prediction. I won't be able to talk about the hybrid evaluation, but it's something somewhat in the same kind of spirit. So think of this as a setup where we have a deep learning model which measures basically X-ray. So in this case, it will be a mammogram screening. So the model actually puts this as cancerous or not, and this is quite important in, for instance, in the UK. So every woman after a certain age, every 3 years are being screened, and the UK, the screening procedure is, there is one first doctor, but then two doctors are looking to the same image, so it's a fairly costly procedure. The idea would be, can you actually replace maybe this by a deep learning system, or maybe make it more accurate? So it's a kind of a screening thing, which is quite, substantially important. So one idea would be, okay, can we learn a model which can actually route in a sense? So given the predictions of the model, can we actually decide when we use the prediction or defer to a doctor? So one of the important points in here, of course, in principle, of course, if you could improve the model, you should, in principle, put it into the training set and actually, make it better. But in terms of, practical constraints, you cannot touch, for instance, a medical model once it is trained. If you want to change the parameters, it has to go through an entire approval process. So in a sense, most of the time, it is a better engineering solution to provide wrappers. In a sense, you have a model, but then you just, patch it to actually get a better result. So that's a practical thing. And that is, in a sense, the constraint in here. Okay. So idea would be, okay, like, can we get better by combining, two things? First of all, human doctors are also not perfect. That is important. They also make quite some mistakes. The model does some mistake. The whole point is basically if there are some subgroups. So here but just for sake of experiment, example I give just age of patient. It could be that the doctor is less accurate in certain subgroups than the other ones. And if you could learn actually this kind of complementarity, and this is, again, a more classical statistical learning problem, then you can maybe improve the performance. So here, the solution basically was using the subgroups not as like metadata. That also helps, but really using the model's output, not even calibrating it, but then conditional of the model output, estimating how accurate it will be when compared to a human rater. So whenever we actually want to find it, we can fit now a classical regression function to that, and then have a simple routing mechanism. Whenever it turns out the model was actually more confident. In this case, it was actually a little bit confident, sorry, calibrated. And whenever it gives a kind of a, output in a certain region, then we can actually arrive at a decision, and otherwise we are deferring to the doctor. And this composite system turns out to be better in terms of this. So let me show, so this is sensitivity. Sensitivity is essentially accuracy in the positive cases when there is cancer. And then specificity is accuracy in the negative cases, so false positive rate in this case. Here is a zoom of this point. So this is the underlying AI model currently, at that time, whatever classifier it was kind of measured. It is actually slightly better than just a single reader. But if you combine those using this particular learned structure, the actual ROC curve actually goes higher. And this red diamond is this result in the UK of the joint. So basically the panel coming together and then deciding whether somebody has cancer. And then if we actually use this as a separate signal, we can further actually increase the detection performance. So those are important findings. These are done with a lot of data, and we could actually show that this was generalizing to many different kind of settings in the US where the screening is different modalities, etc. So there's a Nature Medicine paper where we actually shared this result. So that's a kind of a nice kind of combination of statistical techniques, probabilistic modeling with with some deep learning kind of applications. So basically, in that particular realm, I think I don't want to go too much about whether probabilities are needed, etc. I feel it's an irrelevant question in terms of, are probabilities needed by the models? Well, let the models do whatever they do, but for evaluation, I think for us, for humans, the uncertainty quantification is extremely relevant. That's how we can actually understand complex systems and their consistency. So that's why I want to mostly talk about, kind of applications in evaluating the models. And in this context, I want to talk a little bit about the uncertain ground truth, because evaluating models is if it's a very, very fundamental thing, then we have to think harder for that. Okay. Oops. So this is, in a sense, the motivating example. And this is a use case that we did with a dermatology classifier. Initially, I want to this is an image from CIFAR 10. It's a standard data set. And then the label of this part, I don't remember what the true label, I think it's a cat. But, in CIFAR 10, there are also some leaderboards. So there are models which are actually on a test set, almost come to 99.49, and there is a kind of a lot of models, and you can be, the 20th model or the first model by depending on a very small kind of a difference. So does it really matter? It seems not, but can we quantify that? So when we want to, like how much actually this, these results are important. But that's maybe more like a academic interest, but in practice, there is another application with this dermatology application. So it's a similar thing. Like I show you this image, and the question is this hemangioma or melanoma? Melanoma is an extremely severe condition, whereas the other one is not. So if you want to communicate the classification to the user, you have to somewhat quantify the uncertainty. On top of that, the problem is, if you want to actually deploy a model, for instance, like for Google, because dermatological search queries are quite common, it turns out, you are not able to provide a diagnosis. You cannot say you have this particular condition, so you have to provide, in a sense, a list of conditions. But then the problem arises. So if you say, okay, you have dandruff or hemangioma, but also melanoma, the person, wouldn't be able to actually parse that information. Like if you have as prediction seeing a kind of a cancerous situation, you will be having a lot of anxiety, and even maybe it's just because we want to actually provide a higher uncertainty set to the user. So wherever we communicate actually a kind of a set, so to communicate uncertainty, we have to evaluate also that particular uncertainty in detail. But how do we evaluate that? We have to get, and we have to use human data appropriately, because in this particular case, we cannot do biopsy, etc. with these images. Just you rely on human judgments. Okay. So this is the kind of like, I will go a little bit into how that might be kind of evaluated in standard supervised models. It is very easy. We just have a true label, and we check whether the true label is identical to the prediction that we have. But in reality, when you don't know the physical true label, like in the cipher, we really depend on human annotations. And as we know, this can be biased, the quality can measure, and especially there could be, in this case, a lot of uncertainty because just the poor nature. So that is called aleatoric uncertainty philosophy. So in this case, annotators disagree, but typically labels are curated by, taking sometimes the maximum of this, whoever is voting. But in a sense, this example would be somewhat different from the case where all the raters are agreeing. And that is somewhat not coming into the evaluation procedure. And this might not be much relevant in cipher 10, and I will show you it is actually not. So, so there is a reasonable argument why you can use, just accuracy to rank the model, but does it also hold for this dermatology case? That's another question. Okay, so I'm going. So now let's look to the dermatology case. So doctors, when they provide actually their opinions, they are used to deal with uncertainty. They're naturally doing that. They provide a differential diagnostics, and that's how the labels look like. So the labels look basically every rater. So here, every B1, B2, oops. I don't know what happened. B1, B2, B3, B4, etc. All these are different raters. And one rater is saying, okay, this is most likely this particular condition. The second likely it is hemangioma and melanoma. And there are some cases where, for instance, B4 says, I don't really know. They are somewhat, for me, equally likely. So this could be all these conditions, but I cannot rank them. So this is actually a very natural way of communicating uncertainty, but we have to, in a sense, use that appropriately. Okay. And then now the problem is, if you want to provide a predictions, how do you actually summarize and how do you evaluate a particular prediction set with respect to this complicated object? So that is the question. So in interest of time, I will rush a little bit, unfortunately. But I want to use some examples to clarify the main idea. Okay, so differential diagnostics, we view them as partial orders. So it's a typical rating task. Give you, okay, you see an image and you see you just label here. Here, people just give their opinion as this partial ordering. And then, if we want to actually evaluate our models, we will first basically aggregate those annotations, get a majority. In classical case, we will just compare it to the output. So this particular process has several uncertainty sources. This one is the inherent uncertainty, this aleatoric one, because the image is not very clear. We cannot decide that there is a clear label. It is manifested actually through this, what we call the annotation uncertainty, because the raters looking at it will actually provide conflicting labels. So how can we actually use that in our evaluation? So that is the question. Okay, so I will go over this bit, a little bit, and then, so the key idea is, it's not, that idea is not new, is using actually aggregation, actually using the aggregation function as a posterior. So instead of aggregating in a maximum likelihood sense or some optimization sense, we will actually aggregate in a Bayesian sense, and then we'll do evaluations under this thing. So if the ground truth is uncertain, we will actually model it with a posterior, and when we evaluate the model, we will actually get a Monte Carlo estimate under that particular distribution. And then look how the results look like. But there is an interesting suite, so you can aggregate differently. And it turns out in dermatology, people were actually using this ad hoc aggregation technique called inverse rank normalization. So every partial ordering is assigned a kind of a label. So if cat, dog, bird, you assign 1, 0.5, 1 over 2, 1 over 3. So this is almost like using those as pseudo counts and then aggregating them, and that's a kind of a idea. But this is a little bit unfounded, because if you get a lot of the same kind of ratings, suppose you get 1 million cat, dog, bird kind of orderings, you don't actually get a distribution which is in a posterior centered around that particular sufficient statistic, because what the raters are saying is just this particular permutation. So you don't actually know too much about the probability numbers themselves. You only know that there is a probability distribution which is consistent with this ordering. So that model is the Plackett-Luce model, which is really the probability distribution of sampling of permutation, which is a quite key object, and it's generalization of Bradley, Terry, etc., which is very much used in, also learning from pairwise comparisons, etc. So there is a model which is, and then we will be also using a Bayesian version of that one. I just tell you that although we had gone through this inference, is quite interesting exercise how you can actually then aggregate and sample from the posterior of a Plackett-Luce model. And in the paper we have some practical way. When compared to this inverse rank normalization that people have been using in this field, we couldn't actually see a substantial difference. So for the type of ratings, the results were somewhat similar, but the Bayesian evaluation provided us some extra signal. Okay, so I will just quickly go how we were thinking about this. So think of the formal evaluation. So we have an input distribution, then we have a classifier under evaluation. This can be a deterministic function, which gives us a decision. Then typically we have a trusted rating distribution, and then we have some kind of a test function. For instance, this could be indicator whether y and y hat are equal to each other. So that's the most general way of thinking about evaluating a model. And then basically, if you want to compute something, you are computing this expectation. And this formulation is nice because you can talk about, okay, if I want to do variance reduction, I can look at this, etc. In this case, we want to actually just estimate this, kind of expectation. In typical, of course, evaluations, you assume that your data set is a standard sample from your labels and then inputs, so that's a big assumption. And then given that you plug that in, and then if you want to, for instance, measure the accuracy, it is the equivalence function. So you basically just recover the plain, very simple accuracy calculation. But the problem with that is if you have aggregation, this particular data set that you get is not really a sample from the joint distribution. So that is quite important. And also, we work on conformal prediction, etc. Like, if you want to use it in reality, you see that your calibration set, etc., is not really a sample. So all the theoretical guarantees do not hold. So it's still important to think about the kind of underlying model in this case. So what we are doing in a nutshell is basically we are imagining this quantity. So that's the we cannot do much about the input distribution, but y given xi. Actually, ground truth distribution, trusted distribution, we don't know. We just say that. And then this is replaced by what we call a plausibility. Those are the samples from the posterior of this aggregator. So that is the story, basically. And then that gives you an interesting thing. So I will jump over this example, etc. But to show you a little bit the main picture. Okay, so this is the kind of like the picture I want to focus on. some of the other concepts are in the slides. If anybody would be interested, you are welcome to look. So here, this is a classification problem, say, with three kind of classes. And when you say the model, your model is predicting only one of the kind of classes, it means that you are actually thinking that this particular sector of the simplex is the one that you are interested in. And you are asking, if I would have aggregated, so suppose all the raters give me some statistics, and I aggregate something from the raters, then I'm basically asking that if I have aggregated the raters kind of ratings, will it fall into this particular sector that my model has predicted? Then you would get 1, otherwise you would have get 0. So if you have deterministic aggregation, there won't be any kind of like distribution in your ground truth samples. Then it will be either in this one or not, and you will get a some kind of estimate. But if you now sample from the actual posterior of the ground truth samples, then we see that the model will always predict this one for this particular example, but we can measure that this one is actually, even if you get a deterministic aggregation, most of the time we will actually provide a different quantity. And in this case you cannot, because this is almost all equal probable. But this picture, the next one, I hope it will bring the idea. So, but if you want to now predict sets of 2, which is very important for us, we cannot say a single kind of class, but we say predict a set of 4, or maybe it's a conformal calibrated set. But how are we sure? How sure are we for this particular prediction? Then we can also measure then just a simple Monte Carlo estimate of the sector, because this is now the sector. If I do a set prediction, that is what this is correspond. And for every permutation, or for any sub partial ordering, there is some interesting sector under this particular simplex, and we can do a Monte Carlo estimate under this posterior of the aggregation function. So that is the main idea. So what is the consequence of that? Which is, this picture is kind of interesting. So you can take a particular label. So you can take the true ground truth labels of cipher 10, and there's another data set called cipher 10H where 50 different raters have rated the same examples. And then you can estimate how cipher 10 labels are kind of how sure actually those things are. And we see that for most of the examples, certainty is, so if you predict the most likely label, most of the time you are fine, but there is about 0.2% of the cipher 10 text examples which are actually uncertain. So that tells us immediately that if you want to compare things beyond this particular level, this is basically meaningless. So that is one thing. And then we can do the same thing with the thing like there are indeed kind of a lot of examples, like the ground truth given in cipher 10H is really conflicting with like this rater distribution. Basically what happens is, if you have 50 raters, then your random ground truth labels are actually not that reliable. In principle, you have to bootstrap as well, but it's very expensive, so you cannot do and if you want to bootstrap only if it's 3 or 4, then you wouldn't get very accurate results. So that's the point where a Bayesian analysis becomes quite useful. Okay, so this is a little bit, the story, and basically kind of related to that. The same picture, when we do plot it for dermatology examples, then we see that actually in dermatology, not surprisingly, actually there are only very few cases that we can certainly say this should be the case. So we can actually see now there is so much uncertainty in there that we have to be really careful in doing our predictions. I will just show a final kind of a result, and then so this is the typical analysis or accuracies that we get of a particular model. These are different models that we evaluate, so you typically rank them in this case. So the blue model seems to be better than the other one. And then we can have a reliability parameter. Basically, because we have a base in posterior, we can say, okay, well, we can have some kind of a it's an inverse variance type of temperature type of parameter, where we can say, okay, we trust a lot to the raters or not, and you can play with that. And then by looking to the entire path, almost like a regularization path, you can see that actually if you trust your labels less and raters less, so you see that there is actually not much of a difference between first two models. So this is not really significant, but there's a significant difference. And that, the models kind of converge to each other when things, you don't trust the model too much. Okay, so I think this is a good place for me to start. So to conclude, basically, I feel that there is a lot of opportunity still in using statistical and probabilistic techniques, especially when making it useful for humans and making things sure that things work as intended, and don't care too much how the underlying models are doing their job. So that particular alignment problem needs, in my opinion, really the probabilistic analysis and statistical techniques. So I want to finish at this.
Are there any questions either in the room or online? Please.
Many thanks for the excellent talk. So I have a question that's sort of a general question about the annotation of dermatological images, for example.
Yes.
It seems to me that there's a time dimension for the annotators that introduces another level of uncertainty in that, say, for the annotators, it's very easy to identify melanoma at the late stages.
Yes.
But when the image was taken, let's say it's highly uncertain. Did you jointly model a time dimension in your model to account for this?
No, not for this particular model. I completely agree. This is an extremely important for screening, like in the mammography images, because you are screening the same lady over time intervals. Bringing that information is important, but those are all practical consideration. Will you be having the data? For most of the cases, the data will be missing, but then how you can actually characterize that. Those are all really excellent things that need to be somewhat brought in, but there are some practical, and also most often legal requirements that one has to be. So you have to build, in a sense, around them. So that is the challenge. But that's an excellent point. It definitely is important.
I think, in the interest of time, we'll thank Taylan again